Alkanes are the saturated ones and alkenes and alkynes are the unsaturated hydrocarbons. In this case, this is called as methyl benzene as it is only having one methyl group. Now, if there are two methyl groups, it is called as xylene. So, aromatic compounds, it's not necessary that they should contain benzene ring, but the ones which contain benzene ring are called as benzenoid and which do not contain benzene ring, they are called as non-benzenoid compounds. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry. So today we are back with session 6 of the chapter Hydrocarbons. So in the last session we discussed about the nomenclature of alkynes, methods of preparation of alkynes, the chemical properties as well as the physical properties, also the isomerism in alkynes, right? So we completed all the methods of preparation, physical, chemical properties, all of that regarding alkynes in the last session. So today we are moving on to the last part of your chapter, that is aromatic hydrocarbons. So today we are going to study about what are aromatic hydrocarbons, what are we going to study in that, then the nomenclature and isomerism in that, the structure of benzene, right? Benzene is the most important person here. So we are going to study about benzene and the resonance structure of benzene and the orbital structure of benzene. And the same way we have studied for alkanes, alkenes and alkynes. Here also we are going to discuss the methods of preparation, physical as well as chemical properties of benzene. But in today's session, we are focusing on the details of benzene, right? So let's begin with what are aromatic hydrocarbons. So we have already studied about the aliphatic hydrocarbons, right? Without the ring structures, or they do not have a cyclic structure. That are alkanes, alkenes and alkynes. Alkanes are the saturated ones and alkenes and alkynes are the unsaturated hydrocarbons. So what are aromatic hydrocarbons? You might be familiar with this word aromatic from organic chemistry chapter itself, right? So aromatic hydrocarbons, let's see. These hydrocarbons are also known as arenes. So if you see arenes, the word, don't get confused, it's another name for aromatic hydrocarbons. Most of such compounds were found to contain benzene ring. So it is written here, most of the compounds were found to contain benzene ring. So the question is, does all aromatic compounds contain benzene ring? So it is not like that. There are benzenoid and non-benzenoid compounds in aromatic compounds itself. Let's see, aromatic compounds containing benzene ring are known as benzenoids and those do not contain benzene ring are called as non-benzenoid compounds. So aromatic compounds, it's not necessary that they should contain benzene ring, but the ones which contain benzene ring are called as benzenoid and which do not contain benzene ring, they are called as non-benzenoid compounds. So this classification we have already studied in organic chemistry chapter, right? So some examples of arenes, the aromatic hydrocarbons. Yes, the most familiar one is benzene. The next one on benzene, you have a methyl group. Yes, this is called as methyl benzene or commonly called as toluene, right? And then you have two benzene rings attached together here. This is the naphthalene and this is biphenyl. In all these cases, these are benzenoid compounds. Why? All of them contain benzene rings. At least one benzene ring it should contain, then they are called as benzenoid compounds. Okay, so now let's understand the nomenclature and isomerism in aromatic compounds. Benzene and its homologues are generally called by their common names which are accepted by the IUPAC system. So their common names is also accepted by the IUPAC, so we can use the common names as well. The homologues of benzene having a single alkyl group are named as alkyl benzene. So this is the general way in which we have to represent it, or the name we have to give. It is alkyl benzene. That means this is the structure of benzene. Okay, that is clear. Now we have a methyl group here. So how can we write this in the form of alkyl benzene? Which is the alkyl group here? Methyl. So the name will be methyl benzene, right? Methyl benzene, right? And that is the IUPAC name. And toluene is the common name that we use, right? Now you have CH2CH3 on benzene. What is CH2CH3? It is C2H5. That is an ethyl group, right? So on the benzene you have ethyl. So what will be the name? Again in this format it will be ethyl benzene, right? Okay, now moving on to the next one, that is isopropyl benzene. This is an isopropyl group, right? Only one particular carbon atom is present as a branch from the principal chain. So this is called as isopropyl benzene. Another common name is cumene. Right. So I hope that is clear. So the general formula is alkyl benzene. Now dimethyl benzenes have the common name xylenes. The three isomeric xylenes are So as you can see here, in this case, this is called as methyl benzene as it is only having one methyl group. Now, if there are two methyl groups, it is called as xylene. It is called as xylenes. And now based on the position of the methyl group, whether it is in ortho position, para position or meta position, you have orthoxylene, paraxylene and metaxylene. As you can see here, the two methyl groups are present. So we know that it's a xylene, right? On benzene ring, you have two methyl groups. So it is xylene, but it is present in the ortho position, right? So this is orthoxylene. Right. Now moving on to the next one. This is in the meta position, right? So this is metaxylene. And these are in the opposite to each other. So they are in para position, right? So this is called as paraxylene. Okay. So this is how we name the aromatic hydrocarbons. Now we are going to study in detail about the structure of benzene. Okay, so in aromatic hydrocarbons, we will be focusing on the benzenoid compounds, that is, those compounds which contains the benzene ring. So first of all, to study about that, we should be knowing in detail about the structure of benzene, what types of bond it is forming, whether it is sigma bond, pi bonds, all of that we are going to discuss now. Okay, so by elemental analysis, it is found that molecular formula of benzene is C6H6. That means you have 6 carbon atoms and 6 hydrogen atoms. So the molecular formula is C6H6. This indicates that benzene is highly unsaturated compound. Okay, as you can see, it is C6H6 means there must be presence of double bonds as well. So it is a very highly unsaturated system. Now, how did the structure of benzene, what is the history behind it? From where did we finally end up in the structure that you are familiar with? So let's see that in 1865, Kekulé gave the cyclic planar structure of benzene. So it was already known that benzene is a planar molecule. That means all the bonds of it lies in the same plane and it is cyclic, with 6 carbon atoms with alternate double bond and single bond. So it is a cyclic and planar structure having alternate double and single bond. So as you can see here, 1, 2, 3, 4, 5, 6 carbon atoms, and you have 1, 2, 3, 4, 5, 6 hydrogen atoms and alternate double bonds. You can see one double bond here, next is single bond, again double bond, single bond, double bond. Okay, so it is alternate double and single bond. So this is the complete structural formula and this is the condensed one. You can see it's just the bond line representation of it, right? So you can see alternate double bonds here, one here, one here, one here. So this benzene structure you are already familiar with, right? So the Kekulé structure indicates the possibility of 2 isomeric 1,2-dibromobenzene. Okay, and in one of the isomers, the bromine atoms are attached to the doubly bonded carbon atom, whereas in the other they are attached to the singly bonded carbon atom. So what does that mean? So it is shown that there are 2 possibilities of isomers of 1,2-dibromobenzene. So as you can see here, this is one possibility, this is another possibility. Now what is the difference between these two? Now you can see here the 2 bromines are attached where the single carbon-carbon bond is present. As you can see here, in this you cannot see any double bond here. Another isomer of 1,2-dibromobenzene, you can see it is where the double bond is present. But it is only possible to have one structure. In fact, only one ortho-dibromobenzene could be prepared. So both these are ortho-dibromobenzene, right? Both if these are in ortho position in both of the structures. But in here it is along the single bond, in here it is across the double bond. So only one ortho structure is possible. To overcome this problem, Kekulé suggested that benzene was a mixture of 2 forms. So he told that either it should be here or here. So there is a confusion. Only one form is possible. So he concluded that it was a mixture of the 2 forms. That means, as you can see here, this can be interchangeable. That means, as you can see here, the double bond is present here, here and here. In this, it is here, here and here. So 2 structures are possible. This is what Kekulé concluded. Now, there was a problem with the Kekulé structure. What was it? It led to the failure of the Kekulé structure. It failed to explain the unique stability. Benzene is said to have unique stability and its preference to substitution reaction than addition reactions. So we have already completed alkanes, alkenes and alkynes. So when you check that, you can see that the chemical properties or chemical reactions when we have studied, all of it were addition reactions. But when we are coming on to benzene containing compounds, they prefer substitution reactions more than addition reactions. Now, why is that happening? Kekulé Kecule couldn't explain. Also the extra stability in benzene also he was not able to explain. So the failure of Kecule structure led to the resonance structure of benzene. Okay, even this resonance structure and what is resonance effect, all these we have studied in organic chemistry, right? So the phenomena in which two or more structures can be written for a substance which involves identical position of atoms is called resonance. In benzene, Kecule structures 1 and 2 represent the resonance structures. So as you can see here, this is one structure, this is another structure. These are the two Kecule structures we have already discussed, right? And actual structure of the molecule is represented by the hybrid of these two. Okay, so both these structures are possible. So which structure is the actual structure? This is called as the canonical forms, right? And which is the resonance hybrid of this? We can represent it in this form. That means, yes, this double bond can be present in either of this position. So together we can represent it by a circle in the middle. Right? Okay, so either of this way we can represent it. So I hope the resonance hybrid is clear for you. Now moving on to the orbital structure of benzene. Okay, all 6 carbon atoms in benzene are sp2 hybridized. Now, how can you determine whether it is sp2 hybridized? In this case itself, you can see, okay, 1, 2, 3, 4, 5, 6 carbon atoms are there, and in each of these carbon atoms, you have 1 hydrogen atom each, right? So, as you can see here, there will be alternate double and single bonds. How do you calculate whether it is sp, sp2 or sp3 hybridized? So let's consider this carbon atom. This carbon atom is further attached to how many carbon atoms? It is 1 carbon atom, this one, another carbon and 1 hydrogen. That means it is further attached to 3 other atoms. So it is sp2. Totally, you will get 1s and 2p, 3. Okay. So, in this form, you can calculate. So, this is sp hybridized. So, it's not just in the case of that carbon atom. All the carbon atoms in benzene will be sp2 hybridized. Right. The sp2 hybridized orbitals overlap with each other and with sp orbitals of 6 hydrogen atoms forming carbon-carbon single bond and carbon-hydrogen sigma bonds. Okay, so it forms sigma bond. So as you can see here, the sp2 hybrid orbitals, okay, so the sp2 hybrid orbitals will overlap with the orbitals of hydrogen atom and forms sigma bonds. So what does that mean? In the case of carbon, we know the electronic configuration, it is 1s2, 2s2 and 2p2. So considering the last shell, we know 1 s shell is there and p, how many orbitals are there? 3, right? So what happens is, we just now we discussed it is sp2 hybridization. So what happens here? This s and 2 of this p will hybridize, right? 1 s and 2 p will undergo hybridization and it will form 3 sp2 hybrid orbitals. Now these 3 sp2 hybrid orbitals will take part in the sigma bond formation. So as you can see here, if this is one carbon atom, one of it will form a sigma bond with hydrogen. Another one will form with the sigma bond with another carbon atom and another sigma bond with another carbon atom. So total 3 sp2 hybrid orbitals will take part in sigma bond formation. But now, so now one p orbital is left free here which is not taking part in hybridization. Now that p orbital will be the one which undergoes sideways overlapping and which forms the pi bond or the double bond, right? So as you can see, that is the ones which is represented in the pink form here. So as you can see, p orbital is having a dumbbell structure. So that is what is shown here. So each p orbital of each carbon atom which does not take part in the hybridization forms the pi bond. So that you can see here, this is the sigma bonds which is represented here, which we already discussed. That is, each carbon atom will have 3 sp2 hybridized orbitals which will take part in sigma bond formation. Now about the pi bond, as you can see, how is pi bond formed? It is by the sideways overlapping of p orbitals, right? So as you can see here, one pi orbital will be, pi bond will be formed. Yes, now along these two, you will get another pi bond and here sideways overlapping and another pi bond will be formed. So this is how the structure you can see, right? In this structure which we have written, this is the orbital diagram and here you can see the bond line structure of this. So one double bond here, one double bond in this side, one double bond here. So you got the alternate double bond, right? Now another possible structure also is there. This double bond can shift, right? So as you can see here, now the double bond can be between these two, right? Now double bond here and alternate double bond here. So that structure is also possible. Okay, so these are the two canonical forms, and all together you can represent it in this way. Okay, so again the 3 sp2 hybrid orbitals of each carbon, one it forms a sigma bonds with each of the carbon atoms, and the another third one with the hydrogen atom, and the p orbitals which do not take part in hybridization will undergo sideways overlapping and form the double bond. I hope this is clear. Right. So this is about the orbital structure of benzene. Now the X-ray diffraction data indicates that benzene is a planar molecule. It is a planar molecule. So the data indicates that all the 6 carbon-carbon bond length are of the same order, that is 139 picometer, which is intermediate between carbon-carbon single bond, which is having bond length 154 picometer, and carbon-carbon double bond, which is having 133 picometer. What does that mean? As you can see, this is the structure of benzene, right? Okay. So what does that mean? All of the bonds which is present in benzene, it is having a bond length of 139 picometer, which is intermediate between that of carbon-carbon single bond length and carbon-carbon double bond length. Okay. So carbon-carbon single bond, it is 154 picometer, and carbon-carbon double bond length is 133 picometer. It is 133 picometer. But when you are seeing the bond length of benzene, it is intermediate of that. All the carbon-carbon bonds will be having the same bond length, which is not this as well as this. It is intermediate of those two, that is 139 picometer. Thus, the presence of pure double bond in benzene gives the idea of reluctance of benzene to show addition reactions under normal conditions. So because of the presence of this, it is not completely double bond or completely single bond. Hence, it does not prefer addition reaction, it prefers substitution reaction. Hence, it explains the unusual behavior of benzene. Okay, so this is why benzene is having extra stability because of the resonance as well as the unusual behavior. That means it prefers substitution over addition. It is because of the bond length which is intermediate between that of a single and double bond. Hence, the double bonds which is present in benzene is purely not a double bond. Okay, I hope that is clear. So in the next session, we are going to study an important concept, that is aromaticity, and then we'll begin with the methods of preparation and the properties of benzene. So I hope the concepts we have discussed in this session is clear for you. So that's all for today. Thank you.